Olá, pessoal, boa tarde a todos. Bem-vindos à nossa live especial no canal aqui do HTLV Channel. E hoje é um dia muito especial, não só porque estamos comemorando o nosso primeiro ano, mas a gente vai contar um pouco da história do HTLV. E nada melhor do que a pessoa que descreveu esse vírus para contar essa história para a gente. Então, eu estou agradecendo em português, eu vou depois falar em inglês com o professor Robert Gallo, mas já agradeço muito a presença dele, a disponibilidade de estar aqui conosco hoje. E hoje a nossa live vai ser em inglês, então acho que vocês vão ter que ter um pouquinho de paciência, vocês podem deixar as perguntas que ele vai responder no final, e a gente vai tentar depois, em outro momento, traduzir, deixar com uma tradução aqui, para que as outras pessoas que não entendem o idioma consigam acompanhar o que a gente conversou hoje. Thank you so much, Professor. And I was talking Portuguese and explain how it will work today. And we are very pleasure to talk to you about the HLV history. For us, it's a big pleasure. Thank you so much.
You're very kind, thank you. I think you were going to talk about HTLV rather than HIV.
Yeah.
Okay, right.
So I would like to make just an introduction. So Dr. Robert Gallo, the Homer and Marta Gudelski Distinguished Professor in Medicine, co-founder and director of Institute of Human Virology at the University of Maryland School of Medicine, co-founder and international scientific advisor of Global Virus Network. So it's a great pleasure to have you here today. We are celebrating our first year of the anniversary of this YouTube channel that we created thinking about the patients with HIV to bring more information so they can have a channel to ask for researchers, doctors about this virus. So it's very good to have you here to talk a little bit about how everything started. So it will be very good to have some time with you. Thank you very much.
You're welcome very much. It's my pleasure. So please, you can ask me whatever you'd like.
Yes, sure. We are very curious about the HLV history, so we make some questions, but I don't know if
anything you want. I received some notice in advance. I looked it over fast, and it looked very straightforward. The first question I saw was, when did I realize I wanted?
Yeah.
Go ahead.
To start, we'd like to know when you realized that you want to work with this kind of research.
Yes, I can answer you, but you know that as a child you have many imprints that you don't know if you recall properly, and generally people in the course of time recall it more properly according to their interest. You filter out what's not useful, I guess, to you. I can say in background, my father was a worker who became self-made into a businessman, but he was an expert on metal, and he studied a lot on the properties of metal, and actually he was sent to South America. He was in Brazil, but mainly Argentina and Uruguay. He was sent by the government because he was there to interact with people and to teach about the properties of metals when you mix them, we call alloys. Well, I can say without fully knowing it's true that I saw him studying a lot of these strange magazines. They were science magazines about metal, which I thought, I don't say that made me interested. It just, I saw his attitude about being serious about knowledge, I guess, and new things. But then, of course, I had a very, not of course, you may not know why, but I had a very profound situation in my family when I was young. I was 11 to 12, coming to 13, but when I was 12, I went to see my sister in the hospital at Harvard Medical School's Children's Hospital. Today, it's the Dana-Farber Cancer Center. And Dr. Farber himself, the man who it's named after, Dana is one man and Farber another. He was close to my parents during my sister's illness. She had leukemia, and she had a longer than normal, normal meaning for the time. It used to be pretty certain death in a year. She lived longer because she had a remission from the newly available drugs that were just being tested. And at the time, they really thought when she was in remission that maybe it was cure. Mm-hmm. So I never knew why she was away and why my parents were away. They went to Boston with her, and I was moving around from one home to another home for quite a while, and really didn't know what my parent, they never explained to me, so which wasn't so good. Anyway, when I saw her, instead of bringing her home, she had gone back, relapse, and the leukemia was really incredible. I don't want to spend your time describing what I saw, but it was a very bad picture. And I would just mention one part of it is that she looked at me, opened her mouth, put her arms out, and a big clot of blood came off her mouth in front of me, and I was in horror. But she was, just a mess. It was awful. How that was the effect of the disease and a bit of the chemotherapy, because it was just being learned at the time how to use it, and she was probably overtreated. Mm. But at that period, I had the experience of seeing doctors that were not just taking care of people; they were doing research, which was a new concept to me. What does it mean the doctor's doing research? It's for you and me. It's for the future, right? Mm-hmm. So all the tests being done on my sister were also to learn, to try to help people for the future. They weren't going to help her very much, but it was a concept that was certainly new to me. And I could never forget the event because it was traumatic, but at the same time, it was influential. And combined with that, my father became a close friend of the doctor pathologist who made the diagnosis that she had leukemia. My father at first hated him, and then they became very close friends. And through my father, I became his friend in time. We were close, and he influenced me more. Finally, one of the homes that I stayed at was one uncle whose son is a cardiologist, older than me by a few years. He retired, and we grew up together. But I stayed with their family, and his father, my uncle, was also teaching biology in 2 different schools. And he was a very curious, in nature. And this was of interest without really knowing it, because I really was trying to avoid thinking about this kind of thing. And I wanted not to think about what I was going to do. I was playing basketball a lot. Mm-hmm. And I have to say, honestly, how else did I spend my time? Not well. Pool rooms, shooting pool, smoking and other things, and I have to say, I was dating a lot of girls, but this ended very quickly, really ended when I started to realize it was now time to get serious. So I was now then about 17. And when I was 17, I made all my commitments in my head. That was it. So the background is what I told you. And the commitment was around age 17, when I knew I had to start really doing well to go to college, to go straight forward in what I wanted to do.
It's very interesting to see how good examples may influence people's life, and how your father's behavior towards technology and all the people that you have accompanied during his life. It's very interesting to see. And I think that everyone is really happy that he chose this path.
I wanted to be honest. It's, a lot of real, scientists really, it's by their nature, the curiosity about science. That was not me. I mean, when I was a boy, it was not me. I was into fun.
Yeah. But I think this is also very important because people usually think that the scientists, like, they have a very strange idea of how a scientist is, and they are just like common people that they have a very deep interest in one thing that they pursue.
You should always know that, not always know, you don't have to know, but I should say to you that scientists are different one from another, just as anybody else, a butcher, a barber, a man working in metal, like my mom, or a teacher, or somebody who goes on YouTube. You know, it's very variable. And the classic example I always use is the University of Cambridge. There are two great physicists who made discoveries, and each, made big discoveries. And one was a man named J.J. Thomson. He discovered the electron. And when you see pictures of him and you read about him, it was what people kind of think of as a scientist. You know, he had the little round glasses and white. And I think, as I recall, but I do remember, he looked to me like somebody in a librarian, you know. And apparently he was very quiet and shy and all this stuff. But across the room, across the hall, whatever, nearby, was Lord Rutherford. He got knighted, Lord Rutherford. He was a big, talkative Scottish guy, apparently full of jokes, not always without some, I guess, common words, you know. And they said he was like, he liked ladies and things like that. And so he was a very outgoing man, the opposite of the other one. Yeah. And, what are you going to say? I mean, so you describe the sign, though. There's no way. I mean, there's some things in common. You better know how to work hard, and you better know how to present your results, because they'll die with you otherwise, and then you're not a good scientist, because you're supposed to catalyze getting truth to people as best you can. And part of that is being able to communicate it. Not everybody is effective at that.
It's true. And can you talk a little bit about how was the HLV discovery?
Sure. I came to the National Cancer Institute of NIH, National Institutes of Health, right nearby where I live now, Bethesda, Maryland. This is the major research center, especially for MDs, but also PhDs go there, of course. But MDs didn't have many choices for learning about science research when I started out. There weren't all these special centers of excellence in viruses, or center of excellence in immunology, or in diabetes, a disease, or, like AIDS, or this or that. There were really very few choices, a few cancer institutes, and of course, what I said, the National Institutes of Health. There was also the Vietnam War, and you could go to NIH in place of in your public health, and if you were good enough and competitive enough, instead of going to Vietnam. So a lot of people were applying. It was extremely competitive. And I have to say that, as I recall, almost everyone, not everyone, but almost everyone had come from Harvard Medical School, which I did not. But I came after going to medical school, I came to NIH from the University of Chicago, which also had a strong research reputation. And I was able to get in this very competitive environment. So when I was there, I realized I need a lot of technology experience. So I focused on things that were like biochemistry and the developing early field of molecular biology. And it was the term not really in use yet. And it was really the study of nucleic acids. Let me say DNA, RNA, and things like that. So we're just starting out that way. And I wanted to get experience as much as I could in this kind of basic science, in order to be able to effectively deal with modern science at the time, and to be parallel with my PhD friends. So I needed that background. Then one day I thought, okay, enough is enough. What are my strengths, and what do I want to really do? And I started to study blood cells. I never said I'm going to study leukemia. and I will study blood cells, basic biology. But you know, why blood cells? In my mind, I'm not thinking, but the background, it's leukemia.
Yeah.
And I had a very miserable experience when I came to NIH while learning technology, taking courses. The person I was supposed to work with left. He went to Duke University, and I was alone, essentially abandoned. And the Cancer Institute took me and put me in a clinical ward for a year. And where do you think it was? Children's leukemia. And at the time, there was miserable therapy. And what did we really do? You met with mothers and fathers, but mostly mothers. Fathers sometimes didn't have the strength and seemed to be away or absent. Not all, but many times. And you were announcing after a weekend, your child is dead. This was a very, very bad experience. I mean, because I never wanted to see I never saw patients again after that year. I don't see patients. I mean, that was just it, because, you know, you come out of a place like University of Chicago and you feel very confident that you're really good. You think, you know, in medicine, you know what you're doing, everything else. I mean, I knew I needed the science background. But you don't expect to be telling people that their child is dead all the time, and you're failing and you're failing and you're failing and you're failing. And then actually, one of my associates killed himself. He was a doctor who was so depressed. I mean, took morphine to a hotel and killed himself. It's a very difficult time. They should never take the beginning confident young scientist doctors and say, go here in leukemia ward only. So, you know, it wasn't, now it's a different story. You can treat childhood leukemia very well most of the time, not all the time, not the so-called AML. Anyway, I finished that year. Pardon me. It went, then the next year I was fully in the lab and I started, you know, then I was thinking, I told you, blood cells, not leukemia. But then after a year or two, I got in with a tennis partner who came from China, who was a virus specialist and who knew I was interested in leukemia. And then one day he said, why don't you start thinking, you're interested in leukemia, you've told me this, you really are interested in it, now get involved. And he said, in animals, it's often caused by a virus we call leukemia viruses. In many animals, not all, you know, they knew about half a dozen species, right? They haven't studied many others very hard. And he said that later they would be called RNA tumor viruses when it was realized that genetic information was RNA. But that's true with a lot of viruses today, but we didn't know that then. And then still later, they were coined, the term retrovirus came out. And we can speak about that in a moment if we have time and you want to. But in any case, I said, you know, he's got a point. I need to turn in this direction. However, it was very dangerous because no one believed viruses any longer. They used to believe it, but it was now no longer fashionable. In fact, it was, let's say, highly criticized. To think that cancer could be caused by virus was really stupid, and you know, they're obviously not so infectious, and cancer patients and all that. They didn't really understand the way it was happening, you know. This takes years and years to occur, and it's not the patient who's infects, it's somebody else, and that's when it's early in the infection period. And anyway, it was a most unpopular idea. Worse was retroviruses. They don't exist in humans, as I said. People looked for 20 years. Okay, that's the background. So it was a very difficult time. Again, I was walking into very muddy and difficult water, almost like quicksand mud. But on the other hand, there were reasons to think this way, but I never only focused on that, because I realized to be believed, you have to have some credibility. You have to work on things that are more suitable, that are more acceptable. And so I had a big component of the lab doing other things while I was developing my group. We were publishing normal things while putting 20% to look in this crazy direction. But I had my reasons for looking and thinking about that. Now, we spent, I come to the crux of the issue. The discovery is based on perseverance, and in some respects, a certain faith in what you think and why you think it. Because the objections to me were not good objections. Because nobody found it in man looking hard before, we have better techniques now.
Yeah.
And then when people said, but it's easy when they exist in a species because they produce a lot. But I said, yeah, but those are the species you select to study in a lab. And you don't select a species where it's very difficult, where there's very little virus maybe.
Yeah.
Right? So it was true in chicken. It was true in cat. It was true in mouse, for example. There were lots of virus. So this, and anyway, nobody want to think about, oh, that's BS, that's baloney, this is not going to go anywhere. You're wasting money. And there were people who went to the director of the National Cancer Institute that, this was a waste of money, so it was a difficult time. On the other hand, we were able to persist and have enough support from the directors at the time that kind of believed in the same direction, and that maybe this guy may be right. So we had an adequate research support. Now comes the technology. The two technological things that gave us victory was that I really said I was going to make a technique that would be much more sensitive than the electron microscope.
Mm-hmm.
When you have a blood sample and you're looking for a virus and you put it in a laboratory culture means, you try to grow the cells and you look. I mean, there's no way you can examine, if the virus comes out periodically, which human retroviruses do, we now know. You can't do this by electron microscopy, take a sample, it's probably not there, right? And you go over and over and over again, and you have to quit. It's not a sensitive technique. But retroviruses, by 1970, my friend Howard Temin discovered made the idea that they went from RNA to DNA. He too got in a lot of trouble, but he was right.
Yeah, I can imagine.
And then he was finding an enzyme along with David Baltimore and other scientists in America independently that could make DNA from RNA. We call an enzyme that makes DNA a DNA polymerase. We knew that we had at least 3 of them in our cells, DNA polymerases, but DNA to DNA, the normal cell. This is RNA to DNA. Could I make that test for that enzyme specific enough? And of course, it'll be sensitive. It's an enzyme assay. It's 1,000 times more sensitive than electron microscopy. And of course, you can take samples every 15 minutes if you want to test for the enzyme in a particulate fraction, something associated with membrane. So you tend to culture the cell, try to look at what comes out of the cell or is at the cell membrane, and look for this enzyme. I took years. It wasn't alone. Dr. Baltimore also did some of this work, but we were mainly alone in developing better technique to find reverse transcriptase, okay? And we had to know about human cellular DNA polymerases and their properties so we could distinguish them. So we spent years purifying each of the cellular DNA polymerases of humans, years purifying the DNA polymerase of the retrovirus, that is reverse transcriptase, for many animal viruses. Now we knew their properties well. And we had antibodies that could distinguish them. And we had test systems, enzyme test system for them that could distinguish them. Okay? And so we applied that technique. And then, but you have to be able to grow the cells. And how do you grow human blood cells in a culture in suspension form that you have enough to look for virus, not on a solid surface like a petri dish? That was done, a small amount of cells, no problem, a little bit, and very temporary. We wanted cells growing for a while. We wanted cells in amount. We wanted cells in what we call suspension culture. It's a liquid culture with the cells floating around. And we started to look for growth factors. Growth factors are protein molecules that can make some cells grow. It was only in that period of time that a man named Stanley Cohen and a woman in Rome named Rita Levi-Montalcini discovered growth factors. They got Nobel Prize for it. These were the first growth factors. They were growth factors for epithelial cells, like something. I don't know what cells they actually use. The other and Rita Levi-Montalcini discovered a nerve growth factor. Cohen discovered the epithelial cell growth factor. No one had a blood cell growth factor for cells in liquid suspension like this, right? It was thought that human T cells, the T lymphocyte you hear about in immunology, the T cell, could not be grown. I was listening to lectures like that. It only goes one division and it's finished. So it was not possible to grow that. But we discovered in 1975 and published in 1976, we kept looking in the, how do we look? Let's say I took cells from you, from your muscle, culture your muscle cells, and then I look in the fluid for growth factors. This was the idea we were doing. And we called that, the cells that you put in culture, we called the fluid around it media, the growth, the media. And we took the media and looked for growth factors. And we did it with, oh, I can't only tell you, broke our neck looking and looking and looking. And we made a few discoveries, but the most important one was what we call T cell growth factor. Today it's called interleukin-2, IL-2. Okay, that allowed us to grow T cells. So we were gently being pushed toward leukemias of T cells. All right? Mm-hmm. In addition to that, at the same time, almost exactly, we had people call us that some primates, some apes, were free in the island off of Bermuda called Hall's Island, brought there from Asia, called gibbon apes. I don't know if you've heard of them, gibbon apes. And these animals were getting leukemia. And they're in the wild. They were, you won't believe this, but they were being studied by psychiatrists. I don't know what they were asking the gibbon ape, but they must have been having great sessions. Anyway, we studied the leukemia of those gibbon apes, and we found a gibbon ape leukemia virus for those T cells. It turned out that a Japanese American had just described before this a gibbon ape leukemia virus causing a myeloid leukemia, very similar to human, but ours was causing T cell leukemia. Plus the interleukin-2 is in our hands, T cell growth factor. So we were driven towards leukemias of T cells. So we began to focus on them. A young man from Mobile, Alabama was the first human being from which a retrovirus was isolated. That was our first isolation. We took his blood. We got a biopsy of his tissue because the leukemic cells infiltrate the skin a lot in this disease. And so we biopsied those lesions. Our clinicians did, other people collaborating with me did. And then we got blood from him and his family members. And we were too scared to say we got a retrovirus. We had to do it 2 or 3 times from him, find antibodies specific in him, found antibodies in his family members, realized how he got infected, mama to him, because the whole family born from her were infected. Okay. You can pass it. We realized you could pass it sexually. You could pass it by blood, and you could pass it by what did I say? By mother to child. By the way, that would be important for us, as you know, for our thinking that AIDS might be caused by a retrovirus, because we had this experience. Mm-hmm. CD4 T cells, we found it was attacking CD4 T cells, just like HIV. Mm-hmm. So that set the stage. We didn't realize this virus is endemic in certain parts of the world and rare in the United States and in Europe. Where is it more common? Well, for example, Brazil, for example, Peru, Colombia, of course, Japan, which we knew very quickly thereafter when our paper came out. We made the contacts with Japanese. They had an endemic area in southern Japan and also the northern island of Hokkaido, 2 independent origins. We realized it had a primate ancient origin, monkey to man, long ago. Chimp and monkey to man, at least 3 entries. And it was common in Melanesia, in the Aboriginals of Australia, in certain African tribes and their descendants. It stays within families. We began to learn steadily. Mm-hmm. And their descendants, they can go to one Caribbean island, you have it fairly high. Another Caribbean island, almost nothing. Depends what tribe in West Africa did they come out of, or Central Africa. And it's gone. There's other places in the world we went to. Strangely, Romania and Iran also. We don't understand. Of course, it's scattered in America and in Europe because mainly of immigrants that come from everywhere, right?
Yeah.
America, what is America? It's the United States of everyone. I think USE. I don't know. You can't meet someone and then meet someone else who's from the same place. The ancestors are all different, or parents, or whatever. Right now, in my we have 2 sets of workers around my house, and you talk to them. Actually, the fantastic house men yesterday in my home, both were from Brazil.
Yeah. Nowadays,
Another guy in my yard is Chile. It's not very interesting because everybody's from Salvador. I call it the United States of Salvador, USS. Anyway, I'm getting off the ground. So that's the background of how the discovery was made. And then we spent our time, because I have to prove it to you. We have antibodies in the family. We have repeated isolation. We've now found it in another woman who comes from St. Lucia in the Caribbean. We're starting to put our head together. What's going on? And then we're starting to hear the stories that it's endemic in Japan, and now we're finding it more in the Caribbean islands. So we knew a lot when we published, and we also made sure that it was distinct from every known animal retrovirus. This was not a lab contamination. Okay? So then I took a deep breath, and we were in a position to publish papers, and it was like being in a submarine, fire one. Oh yeah, we'll get criticized for this because we didn't have that. Now fire 2, fire that. They'll still say we didn't have this, fire this.
Yeah, this is what I was about to ask, how this new knowledge, because this is a very revolutionary knowledge, how this knowledge was received among the scientific community.
Well, of course, at the very, very beginning with hostility and still some attack, but quickly that dissolved because we had overwhelming data. Number one.
Yeah.
Number two, Japanese workers got into this independently isolated virus, realized that this is the endemic leukemia of southern Japan and of Hokkaido, the cause of this endemic leukemia. Mm-hmm. So, and then we had a critical meeting in London where if I had any doubts anymore about some aspects of why we found it several times now in the Caribbean immigrants, well, a lot of Jamaicans and I forgot where else they came from in London had this disease. And the clinical people there were aware of it and saying, it's going to be the same disease as the Japanese disease. That's your disease that you're finding. And we would think that's it, and so soon we knew about South America. I learned a lot from your Peruvian friends, Eduardo Gottuso, who had a terrific meeting on HTLV in Peru. And I really had no idea of the amount of HTLV disease in the Amazon in Peru. Mm-hmm. And then figure how did that happen is really intriguing because HTLV2, which we found a year later, is, we found it in a young American man, a Caucasian, and it was strange. Then we found out his girlfriend was an Alaskan Inuit, Indian. And we found out that some Indian tribes had this different HTLV, we call it HTLV2, which is less disease causing. But what good that did is it made us aware that there may be more. So when AIDS came along, we said, So anyway, that it was not received well immediately. I mean, like the first weeks, but this crumbled fast, very fast. It was not true with HIV that when we were thinking immune deficiency, we had people commenting even in the New England Journal of Medicine, well, we're now convinced it can cause cancer retroviruses and they're in humans, but they don't cause immune disorders. Well, that's not true. I was reading everything in animals and they do. Some variants of the cat leukemia virus cause immune disorders. And it was already known by Japanese clinicians that HTLV1 itself, even when you didn't have leukemia, could give immune impairment, not as severe as HIV. So it was not a big jump for us. you know, blood cells, mother to child, CD4 T cells, etc. Okay. Anyway, I'm sorry.
No, it's very interesting. You are just learning with you a lot.
So you asked me about how it affected science in general, or you were about to come to that question, or it's part of the question. How did it impact the evolution of science? Do you want to?
Yeah.
Well, first of all, I mean, what's first of all? I don't know what's first of all. It just popped them out of my head as I think of them. It certainly brought international collaboration for us in many areas of the world. We had no collaborations previously. It certainly brought my group and myself to get together much more with Caribbean islands, South America, Japanese workers, Australian workers. And it gave us an entry into public health for the first time. So it had that impact in a viral disease. Public health, meaning that it's in areas of the global health, I would say, areas of the world that we didn't have that contact with before. And this was a virus that could be spread by sexual contact and by blood, etc. So it had a public health angle to it. I think most importantly, though, it was evident that this virus directly, without any cofactor, nothing else, all you need the virus in a human being can cause cancer. Because viruses or infectious agents causing cancer were thought very important in 1940, 1950, but by the late 1960s, it was finished. Certainly in the 70s, it was finished. It was degraded. Now it was back. And at around the same time, papillomaviruses, which were known a long time, but some were being shown to cause cervical cancer. And little by little, it's true that Epstein-Barr virus is present in almost everyone, but yet with cofactors. It may cause lymphomas, for instance, right? And then there came the hepatitis viruses, and then there came the bacterium Helicobacter. So we went from nothing and crazy to about 22% of all human cancer at minimum.
Yeah.
And I think bacteria will be involved in still more. Yeah, this grows. I mean, in Kaposi sarcoma and herpes virus number 8. So, I mean, I think that's the number one impact. It helped dramatically bring viruses out as causes of cancer because it was just the virus, no cofactor, direct. And the percent of people who get leukemia from this virus upon infection is as high as any carcinogen much higher than smoking, except for asbestos. I don't know anything that causes cancer so well. I know of no infectious agent. What is the statistic? 5% of infected people will get leukemia. But a man named Graham Taylor at Ohio in the United States, I think he comes from England, he's estimated that if you're infected at birth by your mother, then the incidence is 20%. That's enormous. Yeah. Think about that. I mean, a 1 in 5 chance of getting a leukemia from a virus.
Yeah.
If you're born with it from your mother. But it takes time. It's a disease of young adults. People a little bit older than you, people about 30, 35, in that age range.
I like to be a little bit older than me, 35. Yeah. I'm happy.
I said, I assume you guys are in your 20s. Yes.
Yeah. Oh.
Yeah. Well,
we have the same age that your discovery.
I need to look at the screen blown up more. You're in the small picture.
So it will face the wrinkles.
Okay. All right.
So
I think also it made we made a blood test for it that you don't have to be at CDC to do a blood test. We did the blood test for HIV too, as well. So how else did it impact? I think the use of reverse transcriptase as a marker is done everywhere now, with HIV. When we test for HIV, well, now you can use PCR, but if you want the test for the whole virus, you measure reverse transcriptase in an assay. That's how the field was born. So it had impact on the whole HIV epidemic with IDEA. It gave the idea. Yeah. It had impact for technology, for reverse transcriptase. It had impact for technology with interleukin-2, the T cell growth factor.
Yeah.
So it's and the concept of viruses and cancer. That's probably the biggest.
Yeah, I think it changes a lot of paradigms.
Yeah.
So this is like impressive, huh?
Yeah.
Yeah.
It's very interesting.
It brought together infectious disease and cancer much more.
Yeah. Now, can you comment something about the letter that you wrote with Fabiola Martin about the to-who?
Sure, I'd be glad to. I met Fabiola, and I knew of her a bit, but met her and got to know her pretty well in Australia in November of 2017. In the 2017 Australia meeting of the Global Virus Network, which was very important when we were introduced to the Aboriginal people who came to the meeting and gave lectures, 2 of them. They gave a very emotional lecture, very profound and very moving. And they also, the first person at the opening of the meeting looked right at me and was begging for help. So as you know, Australia has a terrible epidemic of HTLV1 in the Aboriginal population, approaching 50% of men and about over 40% of women. Wow, that's extraordinary. Yet, they seem to die, not of leukemia, not of the paralytic neurologic disease which occurs with this virus as well, but with a third big disease. It's bronchiectasis, severe lung disease. So they must be immune disordered, exposed to some bacterium or parasite that causes severe lung disease. And that's totally unexpected. Now, what's unexpected? The high level of infection and the new disease. But in the analysis of the genetic information of that virus carried out in a few laboratories, some of them who used to be my postdoctorals who've done very well in the field since, one of them at the Pasteur Institute named Antoine Gissain, one of them at the National Cancer Institute, Veffa Franchini, who comes from North Italy. They, and at least one other person, have shown that if we can look at the genome as just a straight line, okay? The genes in order. It's the genes at the end of the what we call the three. Oh boy, I don't know how to make this for a layperson. Okay, I better just simply say there's a genetic sequence that shows the greatest variation among HTLV2 to HTLV1. Remember, HTLV2 is less disease causing. Now, Gissain first divided the HTLV into subtypes. We thought they're pretty much all the same. It's not like HIV. But no, with more subtle technique, there's different, you might say, clades, like we call for HIV, or strains, or whatever. And the one causing this disease in Africa is the type he calls C, and the variation is in the same region. We don't understand yet why, what's going on there. But it may be the virus genetic change that makes it cause this lung disease. And the alternative is something we still don't, obviously we don't understand. But this is urgent, and so we wrote a letter to WHO, and we also helped reach the Australian government, which put money in right away to help them with blood testing, etc. So WHO, there's no blame here. It's not blame, because WHO cannot know everything. It has to be reported to them properly. And we probably were never aggressive enough. And so they heard of it, and somebody they talked to, there were no HTLV1 experts within that I know of that were that close. One Australian was who advises them, and he was very helpful. And but they just didn't have it altogether correct. So we wrote the letter, and it changed things. And that shows you that an individual, sometimes can be potent just with enough information. And we have to be thankful that WHO wasn't defensive about it. Rather, they listened, and they thought, and they read, and they changed.
Yeah, it's true. I think that there was like a very good outcome from the letter. that was published, we can see, and I think that everyone, the researchers, people who live with HIV, they are very hopefully that we will see many changes in the near future. Because it seems like that is really like they are willing to do something regarding HIV. And I think we won this for the letter. This was like a very important step.
Yes, yes. I hope so too.
I think so. So they already did the technical consultation, the report. They already had meetings. We are planning a webinar in the World HIV Day, and they are willing to support this webinar to talk about public policies in different countries, what different countries are doing to tackle HIV infections, so one country can learn with the other one, and then we can try to spread the implementation of public policies regarding HIV. So I think this was really very important point, this letter to WHO. And I think we have to say thank you.
Yeah, the credit should go to Fabiola. I remember in history, was it oh gosh, I'll probably screw it up, but the father of Charlemagne was Charles Martel, and he was called the Hammer. Well, if he's the hammer, Fabiola should be the woman sledgehammer.
Yeah.
She's
in a good way.
She's absolutely determined and a force that you're not going to stop.
Yeah, it's true.
So do you have some advice for us young researchers?
I'm not, I don't know what to say. I'm not in any, you could give them advice as well as I can give them advice. I don't pretend to know so much about life that I can presume to give somebody advice. If they want to, if you said researcher, if they're going to in research, and I would say it's generally a happy life, because you get, if you're reasonably open and able to interact with people, there's a lot of people to interact with. It does tend to keep you younger. Your interactions are always with people younger, not young, but some people get older with you, but most of them are going to be a lot younger than you. And there's a joy in seeing, as you get older and it's no longer you can feel like a papa or grandpapa. To see young people that worked with you develop and have success, it's a little bit thrilling and a nice feeling. And if you're lucky enough to find something, it's a funny feeling when you know you found it and nobody else in the world, but you are holding this information right now. We do not have, in my experience, I did not have so many joys of screaming Eureka, because it was human research, and there was always pressure for tomorrow. What's next? It never was a let up. I think I once wrote in a book that there were a couple of years of tranquility, one or two mainly, where you could enjoy success with HTLV1, HTLV2, and then comes AIDS. I mean, that is the end of anything. It's always, what about that? What's next? What about this? What about that? What about therapy? What about vaccine? Why do you don't fail in this? Jesus, it's never ending. So it's not so much that, but normal science people have a lot of. We had joy, sure, of course, and it's and certainly after the pressures of HIV wore out, it's usually many things to be happy about with such a career, and you have to have a persistence, and it helps to be. If you have firm ideas and focus, and the ideas are reasonable, you're going to find something. And you don't want to be stubborn to the point of being silly. You have to have some judgment. But if you have ideas and you're getting support for them, you have to persist. And we could have spent all this time talking about how many failures I had. A lot. I always tell that when I meet with students, a student research day, I always start that way. They love it. They love hearing about your prayers. Wow, I said, yeah, because I'm the complete ass in many things. So, and my first experiments, were, in retrospect, they somewhat ridiculous. I mean, when I was 17, I thought I would go find the function of thymus because I read in an article in a magazine, no one knows the function of the thymus. I said, well, I'll do that this summer, and I took a bunch of mice and sent them to my mother, and she fed them and housed them. And I came home and I tried to take the thymus out to see what happened. Well, they all died. Well, of course they died. I was cutting their aorta and their heart. I learned the lesson. You have to walk before you fly. You need technology. And I will never be a surgeon. I knew that, number 2. And then I knew my mother wasn't the patient, nice lady I always thought, because one day my mice all disappeared. So, I had at least, I could, if we had, time, and it was a silly program, I could name about a half a dozen things, like, as I'm going up the ladder, each one awkward.
No, we have all the time that you want, so we can stay here. And what would you say to people that lives with HTLV?
Wait, I will, since you said we had time, I will tell you one more that's useful. This is useful. It's not exactly funny. This is not sad nor funny, and it might be useful. My first real job, really, I ever had in my life at that time was working in a research laboratory in Philadelphia. Before that, I was really not having any real job in high school or anything else, spending my time hanging around a hospital or just playing ball or whatever. And in that position in that lab, two experiences to share. The first is that when I was there about a week, the technician for the guy, they had moved from Boston, and they had she had worked at Children's Hospital. He had worked elsewhere, but they got to know each other, and she joined him in Philadelphia. Children's Hospital, where my sister was. So this is long after. I'm a medical school now, right? Mm-hmm. My sister's, I don't know when it was, 49 or something, 48, 49. This is now 1963 or 4, something like that. And no, even before, what am I saying? 1959, 1960, yeah. And she said, your name is Gallo. I said, yeah. I heard you had a sister with leukemia. I looked at her. I said, yeah. In Boston? I said, yeah. She said, come with me. I went with her. She had the slides of my sister's blood cells to show. I said, there I was looking at my sister's leukemia. It was a very strange experience. But now it comes back to me doing research. So the boss of the lab had discovered erythropoietin, which makes red blood cells grow. Growth factor, right? The growth factor. Mm-hmm. So, and I didn't mention him, but that was in the back of my mind, blood growth factors, right? Mm-hmm. This was for red blood cells of no real interest to me at the time. But one day when I met with him, he said to me, I want this summer, your project will be go separate all the cells at all stages of differentiation from the bone marrow of a normal animal. He suggested rabbits. I said, what? If you're familiar with bone marrow, the number of different kinds of cells of different stages of maturation are innumerable and many quite similar. How do you separate them all into, different flasks, different tubes? It had never been done, and it's never since been done. I'm a summer student coming to my first job, and there was no more help and almost really no advice. You said, you'll think of a way. Oh boy. So I took the long tubing polypropylene, I think it is long. I made it about so long, and I sealed the end, right, one end. Mm-hmm. And then I took the rabbit's bone marrow as much as I could get and diluted it in media, to make the cells kind of in a suspension, and put it in the long tube. And then centrifuged it at a lower speed, a higher speed, and so on. And then take the tube out, and you could have various levels of where the cells would settle, right? Depending on the speed. And I would cut the tubing so that in each fraction, I might have different cells at different levels of it. But anyway, to do this, and I thought, it's going to have to be very subtle. I need the fluid to be of a specific, of a very defined specific gravity, okay? That means concentration. So now I would use, oh boy, I can't even, how can I forget? Albumin, sugars, and something else that was a big molecule, and I don't remember now. And I would mix various flasks of different specific gravity, okay? To do this experiment with different specific gravity, I would get different bands, right? Well, I did this week after week, and his lab was getting filled with these flasks with different specific gravity. One day, when the summer was half over, he came in, and in front of a nice young lady from Puerto Rico, and in front of another medical student, and another guy working as a resident in his lab, and he started to scream at me. And he said, when the hell are you going to do the experiment? You're making my lab into a glass menagerie, you know? And so I went home, and I have to tell you the truth. I had tears in my eyes on the weekend. I was really depressed. I was ready to quit science. I said, this isn't for me. I just don't know what the hell, you know, I was thinking why I didn't do the experiment. Oh, it was fear of failure, of course. I knew I was going to fail. And by Monday, my attitude changed. I became determined and angry. And I went to him and I said, let's make a deal. I need to quit right now. Or you give me a challenge, you give me another challenge. Let me suggest a challenge, something you like and you would work on together. And we ended up publishing, as a medical student, a few papers with him. He became my major recommendation for getting into NIH at the Vietnam War time, at the competitive time. So I turned a death knoll into a huge victory. It was a study I could handle in a summer and carry over even into my school time. And it was important, and it was rational, and it worked. And we published, as I said, we published papers together on it. It was about chronic obstructive lung disease and what was going on related to why they don't respond, didn't make red blood cells adequately to compensate for the lack of oxygen. What was the defect? And we determined that it was intra-bone marrow hemolysis. We looked at everything, erythropoietin levels, kidney disease, where erythropoietin came from, and on and on and on. Each idea we attacked, right? Okay, that's the story. So what's the lesson for that? I mean, I would think if I'm a young research person and I heard that story, you don't give up, even when you feel like a fool. And one more time, and last thing I'm going to give you from personal life. I'm now at NIH, now in the lab, right? I told you about. And while I'm learning the technology before leukemia, right? Well, I don't know what it is. I was trying to separate the species. Do you know about transfer RNA at all? Have you heard of RNA?
Yeah.
Messenger RNA.
Yeah.
Have you heard of transfer RNA?
Yeah.
Okay, so there's a lot of species of transfer RNA, a lot. No one had separated all of them in any mammalian system. I did that time when I was in that training period. Journal of Molecular Biology, 1970. Pesca and Gallo. You go look it up. It's a long, boring paper. Every transfer RNA. No technical help, just me. Okay, I almost killed myself with high voltage electrophoresis trying to separate molecules. You know, I mean, it's just, the story is the following: when you separate them, it's a big, tall column. You've heard of column chromatography? Well, you separate molecules on these glass columns. You put the sample on top, and it filters through, and it depends what you packed in there, and sometimes they gravitate at this rate, and sometimes faster, some molecules, etc. Right? Well, this was 9-foot columns we used to have. Today they don't go through that trouble. We used to have to drill a hole in the floor above us and get permission from the guy above that we could put a hole in the floor.
Wow.
And so, anyway, it was a beautiful Saturday. I'm at the beach. I'm alone, and I'm got the sample going on there. I really wanted to go play tennis or go swim or do something, or taking all day. And so I put a pump on it, a pump to make it go faster. And of course, it exploded. The sample went everywhere. And one morning, I came to the boss and said, I'm really discouraged. I don't have it in me. I think I'm not going to make it in research. And he said, come with me to my office. Went to his office, and he said, he's a PhD, and he was a big shot. He was the chief of the lab. And he said, Bob, he said, I'm going to tell you a story. He said, there is a young man your age, some time ago. He said he was working in the same lab here, and on a weekend, just like you, he was washing the pipettes. But he put, when you wash pipettes, you put tubing in one place, tubing in another, water comes in, water goes out. Now, don't ask me which end the water goes in and which end the water goes out. Obviously, this young man didn't know, and he had it the wrong way. Okay, so when everybody came to work on Monday morning, this was a Sunday, there was a massive flood throughout the whole corridor. Okay, this young man went to the boss and said he was going to quit, and he convinced him not to. He said, Bob, his name is Arthur Kornberg. Arthur Kornberg was the first person about 8 years later to synthesize DNA in a test tube. He won the Nobel Prize. He was ready to quit. So we all go through, I don't know what the right word would be in Brazilian, Portuguese rather, I don't know what you would say, but think of a bad word. Okay, so that's, you asked, so that to junior researchers, what can I tell you? Persist if you're interested. And it is interesting. And it's a good life, honestly. And you'll meet a lot of interesting people if you're interactive at all. Just don't give up easily or get so depressed or you'll be doomed the very beginning, unless you're really lucky. And if you're working with someone and it's not working, don't be afraid to make a move. You got to give the person a chance, but if the situation is not good, take a risk. Think of, Watson Crick DNA. Watson was in a lab that wasn't working out. He was in Europe. He jumped to another lab. It was Crick's lab. And Crick was not well known. He just felt that they could do something together. You got to think a bit on your own. And it's good to have colleagues that you interact with. Okay, so I don't know what else I can to say to junior people. People living with HTLV, you said, right? What can you say to people living with HTLV? Know the virus, know about it, know how it can be transmitted so that you're cautious in not transmitting it to other people. Make sure your doctor knows of its existence. And if therapy becomes available that's increasingly better as time goes by, which we hope will happen, you're in the right hands then. I think, and then the statistics are still with you. You will live and not die with HTLV. And you will live and not necessarily have bad symptoms with HTLV. If you're one of the unlucky souls, get help, get to the right medical person that has the right experience. If you're in Brazil, which I suppose this is predominantly Brazilian, there are many good doctors. In the Cancer Institute in Sao Paulo is my good friend, Drauzio Varela, could help anyone and give advice about it. He knows about this, and he knows, of course, about HIV very well. So find somebody that knows something about it who can give you advice. And in your local area, they will find you the right kind of doctor. You need to have the right kind of doctor is number one, and you need some education about the virus, number two. That's what I could strongly recommend.
A lot of people sent us questions about antiretroviral drugs for HTLV. So they're always with this question why we cannot use antiretroviral drugs for HLV while we can use for HIV.
It's not the same virus, you know. And the key problem with HTLV is that it doesn't reproduce a lot. I mean, it's not a problem. That's good. It's not like HIV that it's replicating and making variants. You don't have that problem with HTLV. It's quiet. It's already, what it's going to do is probably pretty much been done. It's integrated its genes in your DNA, and it's going to depend upon, well, you say, is there things you can do to slow down the probability of HTLV1 producing a leukemia, the neurologic disease? And I think for the leukemia, we don't know what to say about that so far. There may be nutritional factors. I don't want to say yes. I don't want to say no. There may be cofactors that make it more likely to develop leukemia. I don't know them. I don't know if anybody knows them. And there may be things that slow down that possibility. But you got to stay tuned. Progress is made incrementally in HTLV, but being made. So, the drugs that you'd want would be if you just got infected. If you knew you were just infected last week or 2 weeks ago, yes, there's a period where the drugs might help. But remember, HTLV is strange for a virus. It's produced so little that it's extremely hard to discover it. HIV, much easier. Mm-hmm. HTLV1 transmits mostly with the cell. So it needs to get into your bloodstream, more or less. You need the infected cell. So antiviral therapy, what's it going to do? Very little. Even at the first days, you might get some help, but even then. So forget it. Now, wait, I said forget it, and I spoke too soon. In the neurologic disease, there's a room for antiviral therapy. There's more virus, and there's more danger of the virus, and antiretroviral therapy might be useful for the people that are developing neurologic signs. Certainly, there are approaches for immune control of this. With the neurologic disease, there are killer T cells that are starting to attack our nervous system. And that's an immunological problem of therapy. So you need innovative therapy. We have a Japanese scientist in the institute I direct named Yutaka Tagaya. And he's worked on a small company called Bionis, where they've been working on therapies that are against the inflammatory molecules that are partly, at least, if not totally, responsible for this attack on the neurologic system. So that you have to keep abreast of what's going on and need somebody close to it. In Peru, I tell you, Eduardo Gattuso would know well that. In Brazil, there are HTLV people all over the place. In Bahia, I met several people working on HTLV. You got to stay close to somebody who knows the latest. I'm honestly not the best to know what's the latest on the therapy of HTLV1. You could do better than me. Mm-hmm. But you're not going to, the antiviral drugs for HIV, no, you're not going to go anywhere with it. Okay? So if you'd like a bigger explanation of that, the key one is the bulk of the early infection, and later on, it's just virus-containing cell that is transmitting it. And then when you're getting the disease, it's already too late to do anything with. Okay?
Okay. I have one question. What do you think about the CRISPR technology? Do you know CRISPR?
Oh, CRISPR, I think it's,
yes.
I think it's phenomenal. I mean, it's phenomenal.
Yeah. Do you think it will be useful to retrovirus in the future?
Yes. Yes. I think that there'll be therapies based around it in the future, if that's what you're asking.
Yeah.
Yes, I do. Yeah. Yeah, nice. You may change something genetically that there's minor change. It doesn't do anything to us, but makes us not be infected by a virus, for example. Mm-hmm. Or an integrating virus like HIV or HTLV, maybe you start to attack. If you can do this cheaply and get it to not have side effects, yeah. Could that be a therapy for HTLV disease? Yes.
A lot of things to happen.
But that takes money. That takes a group. That takes a field develop much more active than we have right now.
Yeah.
You know, we made this much progress from Australia, you know, but how far you have to go to develop a field like it's for HIV is here.
Yeah.
You know, we don't have that yet here.
Yeah.
Yeah.
You know, we need more power by Brazil, more power by Peru, more power by southern Japan, more power by the Aboriginals, the Melanesians, Romanians, Iranians.
And I think we need more collaborations as
West
well.
Africa, Congo, etc. Yeah, no, I mean, of course we collaborate, but it's so difficult. It's so
So to have funding, it's very difficult. Yeah.
you know, to convince the National Cancer Institute that this is a priority is hard.
Yeah.
It has to come from United Nations or WHO or something like that, and then the Cancer Institute might move in that direction. They have to respond to pressures they have in America. After all, if you are now in America instead of in Brazil, and you were thinking there's really a high incidence of certain cancers in America, more than you. For example, there was very high incidence of colon cancer. There's very high incidence of breast cancer. Maybe you have the same, I don't know. But there's also very high ovarian cancer, not so much anymore stomach cancer, not so much cervical cancer. But what seems to me to be going up is this brain disease cancer, glioblastomas, pancreas. Very hard to, now, you got your constituency. You're a congresswoman, and you're coming from, let's say, Iowa, middle of the United States. Well, who are you hearing from? Congressman, my family has I have two daughters that are dying with ovarian cancer. What the hell is the NIH doing about that? The congressman can't sit and do nothing and say, oh, yes, they have a bigger problem with HTLV in Peru, especially in the Amazon. It's not going to happen.
It's true.
Yes.
And
Unfortunately, it's true.
What would you say to the policymakers?
Regulating?
Yeah,
doing more.
Yeah.
Well, we're talking about it right now. Noise. People writing in. When it's not, let's say United States was not in existence. What would you do? Where would you go? Well, you'd say what countries are more apt to be doing science like this? Europe, Japan, right? They come to mind. China. How do you get those people interested? Europe has immigrants, quite a number, and Europe has Romania, which has a high incidence, and and as I said, they have immigration from both Africa and the Caribbean with high incidence. Europe and Japan get together. You make noise in both those countries. And Australia, well, how much power do the Aboriginals have in the end? I don't know. South America, you have plenty of good clinical scientists here. Do you have enough laboratory scientists? And can the people make enough noise? Can you put pressure on WHO and on the United Nations if your country cannot do it? You know what I mean? Or cannot influence the US or Europe. I don't think you're going to get a big effort from China. I mean, China has no HTLV. And I don't see them so much working on nobody wants to give credit to George W. Bush. And, I was not always happy with the President Bush, but he created the PEPFAR, the President's Emergency Program for AIDS Relief for Africa. The first dose of money he put in to help Africans, no gain for the U.S. in this, zero. $58 billion. My institute is deeply involved in 8 African countries. The last 2 we added were Malawi and Mozambique. We were very, very heavy in Nigeria. 2 years ago, our institute carried through Dr. Man Chariarat, who comes from Thailand, in our institute. He was responsible for testing every family in all Nigeria. The first study of its kind in history. HIV, everybody was done, every family. So that's 58 billion not million, $1 billion. It's even more now. Even Trump did not push that down. I mean, the amount now, I don't know what it is. It's probably over 60. That's a 5-year plan and renewed every year. No president has touched it. Not Biden, not Trump, not Obama, and not Clinton. Started with George W. Bush. So you get a Republican who has a bit of a heart, who was deeply impacted by Condoleezza Rice taking him to Africa. And then he's very Christian, Bush. Billy Graham visited him. Billy Graham said, "They're our brothers. We say we are Christian. How can we be Christian and our brothers are and we're doing nothing?" You're not going to get that from that many nations, And it doesn't. Does America do it all the time? No. And, it doesn't do it all the time. But it can happen. It can happen. I mean, you get the right president who's having a heart moment, Say, Jesus, this is because there's no gain. We're not getting anything out of this thing, I mean, you know what the end goal is? They want to learn to do the science themselves too, not just help with therapy, not just clinical help, not just epidemiology questions working on together, not just anything like that, but they want to be able to do science in the future. They want to think tomorrow. So we're transferring as much science as we can to them. And our institute is involved in this. At the beginning of the institute, my attitude would have been, oh God, we're going to be spending a lot of time. My thinking would be wasted. We won't be able to keep up in what we need to be doing. But you change your attitude when you see problems and when you see the appreciation. I don't expect this is going to come from too many places. You have to make the problem in Brazil. And I think your greatest ally in this should be Colombia. I don't know how everybody gets along, but Colombia, Peru, and Brazil have a problem. And I think it's probably more than that. You guys just recognize it.
Yeah.
But there's something special about what's going on in the Amazon. That is interesting. But then when I was in Bahia, HTLV was more important than HIV. That was about maybe, I don't know, it could be 10, 12, 15 years ago. They were telling me, you come to the hospital, we'll show you a lot of HTLV patients. We don't have that much HIV.
Yeah, that's true.
You auto-organize, boy. You auto really organize. And push with the discussions with the United States. I mean, Biden is very heartfelt guy, right? You can just see it all over him. If you saw his I guess you might say lecture 4 days ago about the Asian Americans, getting prejudice against. I mean, he was ready to cry. And then he became so angry. He started to scream loud. I never heard Biden like this. He said, "This is America, for God's sakes." He was yelling. He said, "We are everybody. We are the refugees of the world, all of us. Look around. Who here is not a refugee?" He said, "What are we doing here?" He was so angry at some people who had been prejudiced, during the pandemic, and so-called when you say ugly things, we call it, hate crime. Now, I mean, Biden is so upset about that. I mean, you can't believe he is a guy, with the death of his son and other deaths and around him. I mean, he's gone through a lot of grief. So he identifies quickly with this, and he's that kind of person, So I think, and the wife too. So you want to hit while there's the right time. He's the right president to impact on problems of things. He's got a lot of headaches right now. He's got a lot of things to repair, and and we worry about even on the competitive level. America has worries. And there's a lot of things that he's dealing with at one time, no doubt. But he needs a new problem like a hole in the head. But it is a problem.
Yeah.
I mean, if Brazilian leadership could be someday soon in a talking relationship with at that level, I don't know. But first, I think you ought to get the people together from South America who have the problem. The Peruvians surely care a lot. And then you get the leadership there that cares, and you get the leadership here that cares and that understands things, and you find out how serious it is in Colombia, and are they interested? And then I don't think you can go to Venezuela. That would be taboo for U.S. for sure. But I don't know about elsewhere in South America. I just don't even know. I don't think Chile has a problem so much, if at all, or Argentina. But I would wonder about anywhere else.
Great, thank you. Pat, do you want to say something?
Yeah, thank you for all. Thank you for this time. Thank you so much.
You're very welcome. Very welcome. And I wish you both very good luck in everything you do, continued success, because you're already successful. And stay young.
I will try to do this.
Yeah, we'll try. I cannot promise, but I'll try.
So we are really grateful for you to come here to talk to us. I think this was very, very helpful. It was very interesting. So please come back anytime you want. You are more than welcome here. Thank you very much.
Thank you. Thank you. Bye now.
Thank you so much. I'll talk in Portuguese now because we have many questions here, and maybe we can send for you. And
I'll take a few more. I can take some more minutes, but yeah, it's been a while. It's been a while. An hour and 5 minutes. So or more. What is it? No.
We talk a lot, so I don't know.
You can select some of the questions, okay?
Yes, I'll select one because I think it's important because it's about SARS-CoV-2. So let me see if I found here. So we have here. I put here. Can you write?
Make a comment about possible interactions between human endogenous retrovirus and SARS-CoV-2.
I don't know of any such interaction. Although I know what you might be referring to from Rudy Janish's lab at MIT, at the Whitehead Institute, where they think that you may, by virus infection, activate some elements that are part of endogenous retrovirus sequences that would have reverse transcriptase in it. They're not really a full endogenous retrovirus. They're part, and they're repeated in the human genome, like many pieces of former retroviruses that infect and came into our DNA and became endogenous retroviruses, but really ended up, the vast majority, only as fragments of those retroviruses, and some encode reverse transcriptase. And this scientist reported that when SARS coronavirus 2 infects some cells, they activate the expression of some of these sequences, and so reverse transcriptase is expressed. And if reverse transcriptase is expressed, the theory goes, and their argument of some data that they supplied was consistent with that the RNA was being copied into DNA that could be then integrated in our host cell DNA, changing our DNA, not our germline DNA, so it wouldn't go from mother to child through all our tissue, but in the somatic cell that it infected. And would that have some consequences? And that is a theoretical possibility. And so right now, to comment on it is only to say that it is not settled. As you know, I think he's a very good scientist. He's usually very careful, but there are people who don't accept this yet. So I think it's what I can say. The summary answer would be it's premature to speculate further. Okay. I have to guess. I mean, I have somebody that's neurotic and just calling.
One more, just the last one.
Okay, no, go ahead. Sorry.
Do you believe HLV2 is no pathogenic, or we need to search more deeply? Deeply. My English is terrible.
No, it's a very good question. And if you ask me, did our group, my group, or when I was at National Cancer Institute, or now in Baltimore, did we ever do that? The answer is no, very little. We did learn and see that it was endemic a bit in the Inuit population. That explained the guy that we first isolated from because he was the fiance of this young woman who was an Alaskan native. So, but did people look well at the native population? I cannot answer. I can say that there has been some investigations, of course, and they would say that as far as they look, that they never see it causing disease. I mean, the one person we isolated with had a leukemia. It was called a hairy cell leukemia, a hairy T cell leukemia. We looked at some other diagnoses of that, and we never found it in another patient with that, but we only had maybe two, three. So we didn't make a survey. We listened to people that said that they did not see it in any of their leukemic population. And now you can say, well, what about other diseases? Did people look carefully at other diseases? I think the answer to that is probably no. So could we use more seroepidemiologic studies that distinguish HTLV1 and 2 without biasing of what disease? The answer is surely yes. But if you say in the leukemia that we found it in, first of all, it's a rare leukemia, an unusual leukemia, and the people that have looked at the presumed same kind of leukemia didn't find it. Does that mean it won't be in anybody else with this leukemia? No, because maybe it's a subset of hairy cell leukemia. So there's still mysteries of it, but it's not, it's not, to the person who asked the question, it's not such a high priority in anybody's laboratory right now. So when you don't have enough to do, you tend to think of that. But with the coronavirus, with HTLV still burning around, with HTLV1, and with other virus problems, is not going to get a priority that's going to get a good funding score. And in America, if you don't get a good funding score from NIH, which is already exceedingly difficult because the big directors try to use the money in ways that they control, like funding a group. Here's a group of somebody I can rely on, and I can control that group. They're gaining more and more control centrally. So it's not like when I began that young individual scientists had much more opportunity for individual and creative grants. We have to come back to that, I believe, but we're not there right now. So you're not going to see that have any significant priority for funding in the United States. I would say if a country that has endemic HTLV2, should they study it more? Absolutely, yes. But it's not going to come in the near future from the United States.
Okay, that's it. So thank you so much again.
All right.
You're very welcome. If you want to be here again, it will be a pleasure.
Okay. It was fun. Nice to be with you.
Thank you.
Good luck, and as they say today, stay safe.
Yeah, you too. Bye.
You too. Bye. Tchau, pessoal. Obrigada. Depois a gente vai deixar aqui em português. E aí a gente vai tentar traduzir aqui para vocês. Até mais, pessoal. Tchau. Muito obrigada. Bye, bye.